Hello everyone, and welcome to another episode of Cabinet of Curiosities on Our Own Devices. I'm Jean Messier, and today I'm at 17 Wing in Winnipeg having a look at a pair of World War II bomb sights. This is a British Mk.IX and a Mk.XIV vector bomb sight. And these collectively would have been used over a period of around 50 years, from the end of the First World War until the 1960s. Now, before we go into the specific mechanics of how these work, we need to look into why you need a bomb sight in the first place. So in the early days of military aviation during the First World War, most bombing was done manually. So either the pilot or his gunner observer would pull out what was essentially a glorified hand grenade and pitch it over the side onto an enemy position. Simple. And, if you're flying low and slow enough, that's perfectly fine. But when aircraft started flying faster and higher to avoid fighter patrols and anti-aircraft fire, this suddenly was not enough. You needed some sort of instrument to help you bomb more precisely. And this is because when you drop a bomb, it doesn't just fall straight down beneath its release point. It has the same forward speed, the same forward momentum as the aircraft, and will continue moving forward and land quite a distance downrange of its release point, depending on the speed and altitude of the aircraft that dropped it. Now, if for somehow you were flying in a vacuum and there was no air resistance, then the bomb would actually appear to stay directly beneath the aircraft until it hit the ground. But of course, there is air resistance, so the bomb will actually fall behind the aircraft progressively because the aircraft has engines to keep it going at a constant forward speed. And the difference between what's known as the vacuum range and the actual range of the bomb is known as the trail. And if you know the aerodynamics of the specific bomb, and you can test this on a proving ground, you can do this empirically, and you know your actual airspeed, you know your altitude, then you can create a very simple sight that will calculate your bombing range and tell you where to drop the bomb. And this is typically done using what's known as the bombing angle. Since you have your altitude and you have your range, you have a triangle and you can solve for the angle, and then you just set your sight to that specific angle. When the target comes into sight, you drop your bombs, and that is where the bomb will drop. Now, this gets a little bit more complicated if you have wind. So if you have a headwind or a tailwind, the trail will be smaller or larger depending on the velocity of the wind, but you can calculate that as well and achieve, somewhat accurate results. The problem is with these early sights is that you could only bomb into the wind or with a tailwind, and this was not always advantageous to you because on a given day, the enemy would know exactly where a specific bombing attack was coming from. So if you wanted to achieve full operational flexibility and be able to bomb from any direction you wanted, you needed a sight that could compensate for wind drift or could calculate what's known as the wind triangle. And in the wind triangle, you have your ground track on one side of the triangle, and then you have your wind speed and direction on the other. And solving for this produces a course that your aircraft can take so that the wind will actually push it along the ground track that is desired and allow you to drop your bomb on target. So the bomb will be deflected by the wind, but it will be deflected in such a way that it will actually land on target. And the most sophisticated and successful of these early drift sights was known as the Mk.IX or Course-Setting Bombsight, also known as the Wimperis sight after its inventor, Harry Wimperis. And this is what we're looking at today. This is a World War II era Mk.IX. As I said, this was introduced in 1916 and went through a number of different iterations throughout the 1920s and 1930s, and it was adopted by quite a few other countries other than the British Empire. It was, a widely adopted piece of kit and a very successful one. And this type of sight is what's known as a vector bomb sight. As I mentioned before, you plug in all of your different variables, your bomb type and its terminal velocity, your altitude, your airspeed, your compensation for wind direction. Once you have all of these things dialed in, then the sight will be lined up at the angle where once the target comes into sight, that's where you drop your bombs. It will display your actual point of impact. And to show you how that works, let's come in a little bit closer and look at the inner workings of this device. So what's missing on this particular bomb sight is the mounting base, which would have been adjustable in all three axes to keep the whole sight level. And you would have used these spirit levels right here to level the sight. And that could be mounted to a variety of different aircraft in a variety of ways. For example, in a dedicated bombing window in the nose of the aircraft, say on a Blenheim or a Wellington, or on a special side mount on a ferry battle or a supermarine walrus. Now, the main body of the bomb sight contains a compass. This is a magnetic fluid-filled compass, and there's a bellows mechanism inside the casing that expands and contracts with atmospheric pressure to keep the sight filled all the way to the top with fluid. Now, you have a bezel, which can move either independently or be clutched to the compass itself using this little switch right here. And when they're clutched together, you can rotate them using this knob. And there's a whole procedure that the bombardier would have followed, rotating the bezel and the compass independently and together in order to determine wind speed and direction. Now moving forward, we have our altitude post, and this contains the two sighting beads. This is what the bombardier actually would have looked through in order to sight his target. And to plug in the aircraft's altitude, you just would have cranked this knob to move the sights up and down. Now there's two sights because this was intended to be somewhat ambidextrous, to be symmetrical, because depending on how it was mounted in the aircraft, you could have a clear sight either on the left or on the right. And the bomb sight actually would have been issued with a different types of altitude posts depending on what sort of bomb load you had. So it would have been calibrated to the aerodynamics of each particular bomb. So you would have swapped that in before the mission depending on your loadout. Now this is all mounted on this rotating platform here, and this is for use against moving targets. You can move the post side to side, or you can change its angle, and this is to set up the amount of deflection based on the target's speed and course to accurately hit a moving target at sea. And before we move on to the front of the sight, just want to point out an interesting piece of kit that was built in. This little tube right here is actually for a China marker, a grease pencil, and then this little aluminum blade here is for sharpening the pencil. And that would have been used on the bezel for figuring out wind direction, and we'll show a little bit of how that works a little later on. Now, moving forward, this is the auxiliary drift wire, and you would have used this for determining the direction of the wind. So you would have rotated the sight until the ground underneath was traveling parallel with the wire, and that would have given you your wind direction and the course you would need to take in order to overcome it. And then down here, we have our timing beads. So what you would do is you would find a reference object on the ground, and you would pull out a stopwatch, and you would time the amount of time it would take for that object to pass between any two of these beads. And then you would plug that in at the rear of the sight, which we'll look at in a second. Now, this entire arm right here can rotate side to side to give you your actual course, your actual wind drift, and your compensation for that wind drift. So a couple of other controls to look at on the side here. This knob right here is for adjusting the terminal velocity of the bomb, depending on what type of bomb you're using. And what this does is tilt the altitude post forward and backwards to add more or less trail. And this knob right here is for setting your wind speed. And because you don't want that being knocked loose by vibration, there's actually a clutch. So you actually have to push the knob in. And you'll see that it moves the other sighting head forward and backward, depending on the wind speed. It gives you your deflection. And then finally, your last control is for setting your wind direction. And it's this little knob that's on the sighting head. And you'll notice that the faster your wind speed, the farther out this head is going to be, the greater the amount that the arm is actually deflected side to side, which makes sense because you're going to have more deflection based on the higher wind speed. As you can see, that cranks it side to side. And so when all of your parameters are dialed in, your bomb sight will be set up to the point of impact. And you just have to look through this sight, line it up with the little secondary sight, this little cone at the bottom here. And when the target comes into sight within that sight picture, you drop your bombs. So one last component we haven't looked at here is the wind cursor. So this is used for determining your wind speed and figuring out your wind triangle. So once you've done your timing run using the timing beads, you would set this to the number of seconds, and then you would be able to make a mark using your grease pencil in that little loop. So there are a number of different techniques outlined in the Mk.IX's manual for figuring out your wind speed and direction. And all of them involve getting the pilot to fly in different directions, then seeing at which angle objects on the ground will move along these drift wires. And then by calculating with all of those data points, you can figure out what your corrected course is to compensate for the wind. So there's one technique where the pilot would fly in one direction and then fly at 90 degrees. In another, he would fly in 3 different directions, about 120 degrees apart. And then when this was traced out with a grease pencil on the bezel of the compass, it would make a triangle. And then when you aligned the triangle with the direction of flight, it would automatically adjust the angle of the bomb sight. Now, I'm not going to go into detail on to exactly how that works. I will actually link you to a video of another gentleman who goes into detail as to the specific sequence of inputs for actually setting the bomb sight. But needless to say, this was a very time-consuming and very elaborate process, and I really can't imagine having to do this in combat conditions. And of course, if your wind direction suddenly changes on you, as wind sometimes does, then all your setup is ruined and you have to start again. Not something you want to do when you're on a bomb run. And I think this really speaks to this interwar philosophy of the bomber will always get through. When modern monoplane bombers like the Bristol Blenheim came into service, it was assumed that they would always be faster than contemporary fighter aircraft, which they were for a couple of years, and thus that nothing could catch them, that they could just fly straight and level over a target without worrying about being shot down. There was a similar doctrine, especially in the United States, when it came to aircraft armament. They thought that a heavily armed bomber, a flying fortress, hence the name for the B-17, would be able to fend off all fighter attack and then fly over a target with impunity. This turned out not to be the case, of course. Both flak and fighter interceptors quickly decimated daylight British bombers, and they had to switch to flying at night in order to avoid getting shot down. And for that sort of mission, the Mk.XIV was not a good choice at all. It took way too long to set up. It was very finicky. It took a lot of skill to operate, and you could not adjust this quickly if there was a change in conditions. If the wind changed, or you had to fly along a different course, if you had to take evasive action. So about halfway through the war in 1943, the RAF introduced what was essentially an automated version of the Mk.XIV, and that is the Mk.XIV, which we'll look at right now. So this is the Mk.XIV bomb sight, which would have been used by RAF Bomber Command from 1943 onwards. And this particular model is actually a Sperry T1, which is the American-built version. The British didn't have the manufacturing capability to build as many of these sights as they wanted, so they contracted Sperry Gyroscope Company in the States, and they built around 23,000 of these over the course of the war. Now, this was intended to be much easier and faster to use than the Mk.XIV, than the Mk.IX, and much easier to adjust on the fly during a bombing mission. So this sight consists of 2 basic components, the computer and the sighting head. Now, the computer would have allowed you to input a lot of your variables ahead of time, even before the aircraft left the ground. So using these knobs, you would be able to input, for example, the bomb's terminal velocity. And this is based on what type of bomb that you're actually dropping. And there would have been a card for that sort of correction. In this little holder right here, this bomb sight is missing its card. We'd also be able to put in your bombing altitude, as well as the altitude of the target above sea level. And so the computer would then calculate the height above the target. Everything else would be fed in either automatically or by the bombardier during the flight. So for example, this has an air-powered gyroscope in it that corrects for pitch. So even if the aircraft was climbing or diving, this would keep the bomb sight perfectly level. There would also be connected to a gyro compass, typically the one from the aircraft itself, if it was a large enough aircraft like, say, a Wellington or a Lancaster. And that would correct for course. It would automatically input your course information. And then finally, airspeed would be calculated automatically using a pitot-static system. So there's actually a pitot and static port on the side that would be connected to the aircraft's speed indicator system. So a lot of that was already done automatically, and it would be constantly updating itself based on what the local conditions were. And the way it did its calculation is actually kind of weird. I'll open up the back to show you. There's a whole bunch of little bellows, and there would be these little valves that were angled pieces of metal that would be pulled back and forth by these bellows in front of two holes that air would pass through. And so it was a sort of like needle valve. So if you recall my video on the link trainer, the 1930s and 1940s had this sort of love affair with bellows and pneumatic systems. And so here you have a computer that's barely electric. Like there's very little in this that actually works electrically. This thing is mostly pneumatic, which I think is kind of cool. So the computer would feed its outputs via a pair of rotary cables that would plug into the sighting head. If you've ever used a Dremel with a swan neck on it, it's that sort of cable where it can transmit a rotary force through a flexible line. And so let's move on to the sighting head and see how this works. So the sighting head is actually in the stowed position. So I just need to pull out this pin, and that rotates up, and then move this cover out of the way. So the sighting head actually contains its own gyroscope to stabilize it in roll. So between the gyroscope in the computer and the gyroscope in the sighting head, the head would be kept perfectly level no matter how the aircraft maneuvered. There was actually a wide envelope for maneuvering. I believe it was plus or minus 20 degrees in pitch and 60 degrees in roll or something like that. I'll put the actual numbers up on the screen. And this is great because it allowed the aircraft to carry out evasive maneuvers if it needed to without throwing off the bomb sight. Of course, couldn't do too extreme maneuvers that would throw the gyros off, but still it gave it quite a bit of flexibility in combat. Now, the main working end of this is this little piece of glass right here, and that's known as the mirror, and that works in conjunction with this unit. And you'll actually probably recognize this if you watched my video on reflector gun sights, because that's exactly what this is. This is a collimator lamp. So you have a lamp here, you have a mask that creates your reticle, little crosshairs, and then you have a collimating lens that turns it into parallel beams of light and bounces that off of this little transparent mirror. And what this whole thing is doing is it is adjusting the angle of the mirror both in pitch and also in roll, so that when you see the crosshair, it is pointing at the point of impact for the bomb. And no matter how you roll, how your altitude changes, your airspeed changes, all of that is compensated for so that your crosshair is always pointing at the point of impact. And so once you have everything set up, you just need to wait for the target to drift under your crosshairs, you hit your bomb release, and that is exactly where the bombs will fall. Now, I mentioned before that almost everything is done automatically on this bomb sight. About the only thing that the bombardier had to do was to correct for wind drift. And he would do that by uncoupling the head from the base and rotating it so that objects on the ground passed parallel to the sighting reticle. And then that would be input back to the computer. The computer would make the proper adjustments, and it would adjust the angle of the mirror to have the crosshairs on the target compensated for wind direction. So you can see, compared to the WWII sight, this is a breeze to set up. They said that if you had it set up correctly at the beginning, it took maybe 10 to 20 seconds to set this up or to correct for a change in course or wind direction. And you could bomb while the aircraft was rolling, while the aircraft was climbing or diving. It was very quick and very easy to use. It wasn't, however, the most accurate bomb sight. The circular area probable, like the circle in which the bombs are likely to fall, was around 1,200 meters. However, at that point, the British didn't care. They were doing night bombing missions where they were using pathfinders to mark the target with flares. Later, they were using H2S radar and oboe and all sorts of other navigational aids. If you're firebombing a city like Hamburg or Dresden, 1,200 meters is perfectly fine. And in fact, The Norden bombsight, the most famous bombsight of the war, although it had a very good circular area probable in testing stateside, once it got into combat, even in daylight, it didn't have accuracy that was much better than the Mk.XIV or the Sperry bombsight. So that's why the British preferred to use this, because it was a lot faster and a lot more flexible to use than the Norden. Now, this particular sight was actually very long-lived. This continued in service after the war with the V-bomber force, so the nuclear bombers that the British designed, the Valiant, the Victor, and the Vulcan. And in those, the bombardier didn't even have to correct for wind direction because it was plugged into the bomber's very sophisticated, though mechanical, navigation system, as well as ground Doppler radar that would have figured out what the ground speed of the aircraft was, would have figured out its course and everything like that. So everything was automatically fed into these bomb sites, so the bombardier really didn't have to do much except select a target. And so those would have remained in service along with the V-bomber force until it was retired in the 1960s. So very successful design. So one last piece of equipment to show you. This is called a bomb distributor, and this would have been part of the Mk.XIV bombsight. And its purpose was to coordinate the release pattern of the bombs from an aircraft's bomb bay. A couple of reasons for doing this. Number one is to maintain the trim, the balance of the aircraft. You don't want to drop all the bombs on one side of the aircraft and then drop all of them on the other side, because then your aircraft is going to roll quite severely. So this allows the aircraft to maintain an even trim while releasing its bomb load. The other reason could be for the specific type of target. If you're bombing a railway line or you're bombing targets that are, a specific distance apart, the chief bombardier could take these and set the timing of the bomb release to ensure that the bombs would have the greatest possible chance of hitting all of those targets. And so this unit was actually removable. I have the carrying case for it. So they would be removed from the aircraft, taken to the chief bombardier. He would set all of them identically, or sometimes it would set them differently for different aircraft, depending on what he was trying to do. And then they would be distributed back to the aircraft and plugged back into the Mk.XIV system right before a mission. So not really something you typically think about, the actual release order of the bombs, but it's a variable that had to be accounted for, and this piece of equipment is how you did it. So even though the Mk.IX and the Mk.XIV were the most common bomb sights used by the British, they did use a couple of other models, including the Mk.III low-level bomb sight. And this is used mainly in the maritime role for attacking ships and submarines at low level. And how this worked is that it would create a reticle of continuously scrolling horizontal lines, and the speed at which those lines scrolled was adjusted based on the speed and altitude of the aircraft. And how you would use this is you would wait until one of those lines started moving at the same rate as the target beneath you when their speeds matched up, then you would release your bomb. That would give you your correct bombing angle for that speed and altitude. And that was also a very long-lived piece of equipment. It was used in the Avro-Shackleton maritime patrol and anti-submarine aircraft after the war, and remained in service until the 1990s when that particular aircraft was retired. Now, the British used also a completely different style of bomb sight called the stabilized automatic bomb sight. And this is what's known as a tachometric sight. Now, I mentioned before that the Mk.IX and the Mk.XIV are vector bomb sights. They calculate the point of impact at any given point in the aircraft's flight. And as soon as the target comes into the crosshairs, you release your bombs, and that's where the bombs will hit. A tachometric bomb sight works a little bit differently. It actually tracks the target on the ground. You align your crosshairs with it, and then you compensate for any drift caused by the wind and other factors so that the mechanism can actually keep a track of the target. It knows where the target should be. And if you've done your calculations right, as soon as where the target should be aligns with where the bombing angle is, then the sight automatically releases the bombs. And that's how the Norden bombsight, the most famous bombsight of the Second World War, operates. It's also how the stabilized automatic bombsight works. Now, unfortunately, Bomber Command really didn't like the stabilized automatic bombsight because it was a bit too complicated and slow to use. They were perfectly fine with the Mk.XIV. It was fast to set up and it gave adequate accuracy for night bombing missions. However, there was one unit in the RAF that did use the stabilized automatic bomb sight, and that was 617 Squadron, the famous Dam Busters. And they used the sight to make daylight precision raids using the Tallboy and Grand Slam earthquake bombs against fortifications and viaducts and big entrenched targets like that. And using this bomb sight, they were able to achieve accuracies of around 91 meters from 15,000 feet, which is very impressive for the time. Now, I know what you're thinking, the big elephant in the room. Well, what about the Norden bomb sight? It's the most famous bomb sight of World War II. Why aren't you talking about that? Well, I was originally going to talk about the Norden in this video, but then I realized the Norden is a whole other kettle of fish. It works in a very different manner to these two vector bomb sights, has its own fascinating history, and I'd much rather wait until I have access to an actual Norden to show you how it works. So maybe one day, but not now. I think this video is long enough and there's enough fascinating history and mechanics behind the British bomb sights. Anyway, that's all I have for you today. I'd like to give a big thank you to Mk.IX to lent me these two bomb sights, as well as Gord Crosley and the rest of the heritage staff at 17 Wing for allowing me to film here and to have access to a whole bunch of other cool artifacts that you'll see in upcoming videos. Until next time, I'm Gilles Messier from Our Own Devices. Have a great day.